let's get started. Yeah. Okay. So welcome everybody to our slightly delayed Nexus seminar this week. We have our own Huolin Jin from our own physics department, who did give a talk here about a year and a half ago, but has new stuff to tell us about, but we'll also go over a lot of the earlier stuff as well. So Huolin came from Brookhaven National Lab. When was that, Huolin?
So that was 3 years ago. So actually, I worked there 2013 to 2018.
Okay, so you're there for about 5 years,
yeah.
And then you came here about 3 years ago. And of course, he's done an amazing amount of stuff in electron microscopy. And what he'll be telling us about is, using machine learning within electron microscopy. And not so long ago, he won a DOE Early Career Award here. And I believe you got tenure.
Yes.
Just last year. So congratulations.
Thank you.
Yeah. Okay, so please take it away, Huolin.
All right, so share the screen. I want to thank everyone for being here. Let me see. All right, you can still see the slides, right?
Yes.
I believe so. Okay, great. So my name is Huolin. I work in the physics department here. So today I'm going to cover the things I talked about 1.5 years ago, and a little bit of new things. For example, how to compress and basically decompress big data streams very efficiently, even at very high compression ratios. I'm going to cover some of the basics. Basically, in the case when you have computer vision data, how you actually create ground truth labels properly, such that you can train your network. And I'm going to also talk about image restoration, in-painting, and how it can be applied to three-dimensional imaging. All right, so just briefly about transmission electron microscopy. Just like optical microscopy is, you have a bunch of lenses. Conceptually, you have an object here is really thin, is electron transparent. Basically, when high energy electron impinge on it, it can actually pass through it, and you have both amplitude and phase modulation. And then you have a lens, and of course here is not an optical lens, it's not a glass lens, it's an electromagnetic lens that will bend the electron in a way very similar to optical lenses, except that it has very large spherical aberrations, right? So, and then once you pass through that, and actually in the real microscope, we have a series of those lenses that actually translating the images and finally put it on, for example, a scintillator, and then later it can be digitized into an image, right? So this is, how atomic scale information gets magnified and finally image that you can see. I'm going to show some images later, right? So, and of course, we can also operate and the microscope in a so-called scanning way. Basically, we focus the electron beam prior to the sample and scan it on the sample at the atomic scale. That will also build up atomic scale images by collecting the scattered electrons. And also it can give you chemical information. These are called electron energy loss spectroscopy. That's very similar to X-ray absorption spectroscopy. You have these discrete edges that come from the characteristic core levels that excites into the conduction band of your materials. And with that, we can build up an image at the atomic scale of, the composition, the concentration of the atomic species. It's sensitive to both heavy and light elements. So this is the thing that we can do with electron microscopy. We basically can magnify nanoscale images and look at their atomic scales, right? So what the future of this this field is going to be, in my shallow opinion, is that we're going to have autonomous TEM. So basically, hopefully in the future, all our chemists and materials friends, they don't have to really ask their students to go into the lab to make material. They have robots to do this. You only need to program them to do that, and then the sample gets translated into the TEM by a robot as well. And we have automated data acquisition for both ex situ and in situ experiment, right? Ex situ experiment is that you look at the sample in a static state. In the situ experiment is that you supply stimuli and watch how your material changes. So hopefully it can do both of that. And you have automated data analysis, give you multi-scale information. In the TEM, we can go from multiple micron scale down to the atomic scale. And report the norm, average what your material look like. And also report heterogeneity, right? So this is really what we want, is that we don't like the student to cherry pick the data. We want the whole picture. We want to know both the norm and also the standard deviation. Okay, and hopefully can write a tech report, a paper for us, right? And that is the hope. We will achieve that in the next 20 to 30 years. And of course, we're currently in the state we have deep learning, which is the weaker framework of artificial intelligence. To fully achieve this might be very difficult. I'm gonna come back and talk about why it is slightly difficult, more difficult problem than autonomous car in the next few slides. So here are some of the automated in situ experiments we have already been trying, and conceptually it's pretty simple. You just track the area, right? In the TEM, when we heat up the sample, because even though we're actually heating up the sample locally, still there's thermal expansion. So during these experiments, your sample drifts out of the small field of view we have. This is a low mag, and you have about 50 microns of field of view, and we zoom all the way down to the nanometer scale in the TEM, right? So basically, easily, within half an hour, the sample would drift out of this field of view. So what you need to do is actually track it over time, and it's fairly simple algorithm to do that. Cross correlation can do it pretty well. And of course, we put down a few anchors so we actually can go down some of the characteristic sites and actually take images from those locations and higher mag. This is basically what's happening if we're able to track this material over 6 hours and look at, during heating, how oxygen loss induce all of these pore formation inside the samples, right? And of course, we want to take images at atomic resolution. On the left, this is an area where you have the pore generated, and even though it's only 100 nanometer, it seems small, right? The field of view, but to the electron microscopy, we want to look at atoms, and atom to atoms distance on average a little bit larger than 2 angstroms. That means you need a lot of pixels to actually resolve that. So this is a montage of 100 atomic resolution images that actually give you, enough resolution to see those atoms and over 100 nanometer area.
Sorry, Jean, can I ask, the white spots, are they individual atoms?
They're individual atomic columns.
Columns, okay.
Yeah. So they're not individual atoms. There are individual atom columns. So this is a periodic crystal you oriented such that onto a so-called zone axis, and you have a columns of atoms that are aligned.
Right. And there's
off axis depending on the resolution. This contrast will see out, and you don't see it.
And there's about 3 or 4 of them in this picture. Is that right?
Oh, so here I believe you can see a lot of these atoms, right? So here, unless you know, so these are all atoms.
Oh, okay. I'm confused. It says, oh, 2 nanometers is just the size of the bar, not the size
the
of
size of the bar.
Oh, okay. I was right. I thought it was the size of the picture.
So each bright
okay.
dot here is a column
Yes.
to that.
Okay. Thanks. Thank you. That was it. Yeah. Okay.
So okay, so these are the kind of the automated experiment that we can do now to basically we don't need a person to be operating the microscope over. This isn't actually an overnight experiment. We came back the next morning to actually collect the data to look at the data that has been collected overnight. All right, so this is very important. I mentioned is we want the norm, we want heterogeneity, right? So, and in the TEM, this is a multi-scale problem, right? So it starts from the scale on the top left that's where you have the TEM grid. That's where all your samples is actually sprayed on, and you basically starting from that grid, that scale, 3 millimeter in diameter, all the way to this tens of nanometer length scale. For now, we can take about 5,000 STEM images per day. And if it is you're running your detector, these direct detection detectors at full speed, you basically can generate almost petabytes of data a day. And the good thing about here is that if you do it in this approach, there's no cherry picking, meaning that you can statistically sample all your samples. And however, to do that, you need classification and clustering analysis and all that, because to sample a 3 by 3 millimeter area at a pixel size of a 0.1 angstrom, you can calculate how long it would actually take for that to finish. It would take almost not some task that can be done in a reasonable amount of time, right? And of course, in cases you really need to the three-dimensional shape of the material, you need to do electron tomography and all that. So this is basically a multi-scale problem that we're facing in the TEM, right? So the challenge here is that for the TEM, unlike the ImageNet, has already been created by actually interestingly by computer scientists. To actually train out this network for the TEM, we don't have a TEM ImageNet. All right, so that means you don't really have a library of images that for you to actually do classification, object detection, healing, restoration, all that you want to do for autonomous driving, right? And the next problem is with these really fast detectors, you almost generate too much data. And the question is, how do you efficiently compress it on the edge and decompress it later at a speed that is reasonable? Okay, and how to go to higher dimensions, basically three-dimensional imaging, right? So the solution now we have is the weaker framework of artificial intelligence. I'm going to talk a little bit about that. Before I talk about neural network, I want you to look at this image and appreciate how fast your brain can process this image and telling you it's a digit 3, right? So we have different versions of digit 3, and our brain can process instantaneously and know they're all 3s. Although they look different, we know it's not an 8, it's not a 7, right? So this is basically how our brain can function, can recognize these images very fast and very accurately, and also precisely. And the thing is, okay, so if we can digitize this image 28 by 28 pixels and put a grayscale intensity in it, how do we actually classify it such that it can tell us is 0 to 9? Right, so that is basically what machine learning and specifically here neural network can do. Mathematically, it's fairly simple. Inside the bracket is just a linear sum of the previous numbers in the previous nodes, and weighted by the weights. That's basically the connection here. And if you want to add a bias, you can add one. And the operation that's operated on it to make it different from the linear type of a regression is that here you actually have a nonlinear response function, activation function here. And that makes neural network is special and makes it actually different from these linear machine learning methods. All right. So here is basically a digit 7 that passed through a network, and hopefully we want number 7 to light up. And the question is, what are the networks that we can use now for different type of applications? And we know CNN, the convolutional neural network, is good for image recognitions. And if you are working on time series analysis, the long short-term memory network is good for speech analysis, good for time series, good for predicting, the climate, for predicting the stock market as well. For neural network for today, I'm gonna just talk about the plain vanilla version of a neural network. In old literature is called multiplayer perceptron, and it's a fully connected neural network structure. And here the question is, if you call a neural network, what are neurons, how they are connected, right? So a neuron is the thing that just was made up by the machine learning people, right? It's a unit that holds a number, and basically here, the number that's actually stored in it is called activation. That's basically is a way to kind of simulate, in our brain how these synapses, neurons are connected and activated. And that's how this activation word came in. It's just a normalness number between 0 and 1, or you can just view it as intensity in this image, right? So then the question is why we have these layers, particularly what are these middle layers doing? The first layer is basically your image gets passed in. The last layer are these classifications. So what are those latent fields? What are they doing? So let's look at how our brain conceptually actually classify those images. Let's have a number 9. So it has a top circle, it has a vertical line, right? Number 8 has 2 circles for 2 vertical line, 1 horizontal one, right? That's how our brain actually processes them into different segments. Essentially, in the latent fields or in the middle layers, the one that's closer to the final layer are storing these high-level features, right? So basically, when we have number 7, the top circle and the vertical line will actually light up. That's conceptually how this neural network is supposed to work. And of course, in the previous layer, things are going to be a little bit different. Everything is going to be not as coarse grained, it will be finer. So basically, partition this circle into smaller segments, and they're stored in the previous one. That's a low-level feature, right? So basically, the neural network is passing the information from low-level feature to high-level features, and finally reaching, number 9 being classified that will light up. And essentially, in this very simple neural network, problem, you have a total of 13,000 degrees of freedom that you can actually adjust, right? And such that it will actually function conceptually in the way that I just presented, like our brain actually partition an image, right? And that training or learning process is basically finding the right weights and biases, right? And to do that, you need to train the data. You need to train the neural network such that it will find the correct weights. And the most important thing is actually to create ground truth labels. So let's look at how we actually can create those ground truth labels for supervised learning, right? So here's a way to actually simulate or generate a realistic TEM images, right? So in the TEM, we're looking at those atomic scale images. And as you can see here, this is an image that without any noise, you have these atomic columns that's aligned. Typically, we're doing counting experiments. That's where you have Poisson noise. That is really a noise that statistician and mathematician don't like because they don't actually have a good closed form to incorporate that in their regression and Bayesian problem. Unfortunately, and this is where actually neural network is good, that can implicitly actually incorporate that in the neural network that was trained. And of course, we also want to generate those tearing that's actually present in our TEM images. Once you add all of these in, actually these images are becoming sufficient to actually train our neural network efficiently. And of course, for the community, we have built a TEMimageNet where we have 13,000 entries, 10 types of ground truths, and everyone can download it and use it to actually train their neural network or benchmark their neural network. And this is our first iteration of training, and we found that the left are the images, the middle column here, that's the ground truths, and third column are the results that's spilled out from the neural network. And it kind of works, but it doesn't work really well because, for example, here the brighter and the dimmer atoms, they're supposed to give the same size, but the network here does not. So that's because we use incorrect learning, and the neural network during the optimization process get trapped in the local minimum, so it doesn't actually reach the global minimum, right? So this is where for the student, the choice of optimizer is very important. The good thing is there are a lot of information on the internet that you can just do a little bit Google. So you can set up your learning rate correctly, or you use those better, more automated optimizers that can basically help you to get to the optimized states faster and also more robustly. Right. So if you do everything correctly, here are the improved optimizers with the improved optimizers. On the left, these are the images, and we have the segmentation with atoms. We have the super resolution processing and also localization. They work really well on those images that are so-called borderline, has borderline good signal noise ratio, which is typically 20 dB. Some of those are actually below that, right? So, and of course, the test is really to test the neural network on images that it wasn't trained on. So our neural network are trained on simulated data, right? So the ultimate test is experimental images. Right, here are some examples. On the left, you have a Cobalt 304 spin now type, right? And here, this TEM is a little bit low in resolution. So it doesn't really resolve the 3 atomic column here, or barely resolve it. And you can see after use the super resolution processing network, they actually work pretty well. So the 3 atomic columns are resolved with very high confidence. And here is a lithium titanate. It has a surface as a little rock salt structure. Inside is, you can still call this a spin-out structure-ish. And basically that can localize all the atomic columns correctly. And this is actually a scenario where I really created this tool for is when we work with nanoparticle, we want to know where the atoms are on the surfaces. That's where the catalytic property really the structure on the surface really matters to their calculated properties, right? So, but often we don't have very good algorithms to actually determine these atomic coordinates on the surfaces because the contrast is much lower than that of the interior of the particle. So here I can see the neural network perform pretty well on these cases. And of course, you can do a lot of creative things, determine the strain field, finding some of the atoms that are supposed to be in the transition matter layer, but hop into the, in this case, lithium layer. So that degrades your lithium ion battery, right? So, and here, this is where I call, this model is a real success. This isn't an image that even I just by my eye, I have problem telling in some cases whether I have an atom or not, but with this tool, it can do it pretty well. So of course, you can process image streams and all that, right? So this is the first example. Just want to show you that actually by smartly creating ground truth labels, creating a reasonable library, you can actually train your network to perform a lot of things that traditional machine learning algorithm actually fail miserably. For example, denoising, super resolution processing, and all that. So here's another example I want to show, right? So many of you have probably heard that 3 years ago, CrowdEM won the Nobel Prize. The method they are using to actually reconstruct the three-dimensional electron density map of, well, in this case, not electron density, I need to be careful here, is actually the nuclei density map of protein is by doing the so-called single particle reconstruction, where you take 1 million copies of the same protein or same copies of the protein, and then you figure out in which orientation this image is taken from, and you do the three-dimensional reconstruction, right? So the same thing can be applied to nanomaterials as well. If you imagine on the right, so this is a model system where you have a little ball inside a frame. This is a three-dimensional object, and if I'm able to actually collect images of this object that's randomly distributed, then I will be fine. I will be able to actually reconstruct the three-dimensional shape of this object, just like single particle reconstruction. The protein, the structural biology do. Right. One of the problems that we found is if we only look at those isolated particles, they all sit flat on the TM grid, right? Just because it has a flat surface, and that's where it anchors on the substrate, right? So then, okay, you break the requirement of single particle analysis, where the distribution of these particles should be random. The orientation distribution should be random. So then we look into this a little bit more and find, okay, this particle, when they aggregate together, they tend to actually start giving you a distribution of their orientation that's slightly more random, right? So the next question is, okay, we need to go to these aggregates, and how do we actually segment out those particles? I don't want to do that manually. I don't want to do that by hand, right? So we have to be smart at creating a machine learning model to actually do it automatically for us, right? So immediately I turn to deep learning for help, right? Because it's pretty good at doing segmentation. So here are a couple, ground truths I first created, right? So you can create a mask. You can create basically there, you only segment out where the boundaries are, right? And then you start putting them together into images, right? And then you train a neural network to do either, find a segmentation mask or finding the boundaries. And here's after training. And then you apply to the real experimental images, and you find, okay, it fails miserably. They don't get segmented separately, right? You see all of these particles here, they're connected. You want them to be disconnected, right? So this is not doing me any favor. And here, I want their boundaries to be highlighted so I can segment them out. But here, there's no intensity between the boundaries when they're attached together, right? This is because in my training set that are put together, this is simulated data, their boundaries don't exactly look like the experimental images. So what can I do? Well, I'm not smart enough to actually, in this case, create a simulated data set that look exactly the same as the experimental images. So should I surrender and say, okay, hire undergraduate student and say, okay, go hand segment 1,000 particles for me? No, I'm not going to do that. Right. So here's actually a tool that you can use. It's called instance segmentation. Right. So traditional segmentation is that you have, for example, 2 objects and both of them are segmented in the same mask. Right. The instance segmentation is actually for each person that's actually appear here, they're going to be segmented separately rather than having just one lump sum of, here are 5 people that you don't know. Actually, there are 5 masks that are present here, right? But using instance segmentation, then I can actually start doing fairly sensible segmentation or isolation of these particles. But I still have, some false positives here, right? How can I deal with that? You will, when you work on these computer vision problems, you will, realize you have these problems as well, right? That's where you need to actually start further augmenting your images, right? And you want to put some low frequency background into your images such that your neural network become robust to those signals. And then after that, right, we have a very low false positive rate, and we can actually utilize that to actually reconstruct those the 3-dimensional shape of this using a single particle reconstruction. All right, so this is just a second example how you actually can utilize some of the, for example, instance segmentation together with a reasonable augmentation of your data set, so you can actually perform some of the tasks that you want to perform in computer vision, right? All right, so next is we talk about big data, right? So in the TEM, we're really generating big data. Some of the detector, for example, directed detection detector can generate 13 gigabytes of data, not bits, per second, right? So in 15 minutes, you're gonna fill a 4 terabyte high-speed disk array, right? That's basically you might have like a 2 terabyte of RAM as a buffer, and it still need to dump it onto a high-speed disk array. Typically, these disk arrays are a SATA 0 setup of 8 hard drives that's consecutive, that's are storing data in stripes, you have a limitation as how much you can actually do with this type of a throughput that can dump these data. Typically 4 terabyte are those that you can afford, right? So, and then you find, okay, even if you can increase this, you got to store your data somewhere, right? You cannot just have like 10 portable hard drive, each only reads data at 100 megabytes per second, and you realize, so do a small calculation and you find it, you need days to actually to even take the data out, right? So the offloading the data becomes a bottleneck, not to mention the analysis, just to offload it somewhere. Even if you are optical fiber connection to your big data array, is still very slow, right? So this is where we say, okay, we got to compress the data, right? So the thing here is that we're generating data at 13 gigabytes per second. And you can't do some of the sophisticated, for example, JPEG type of compression at that data stream with FPGA, free programmable computing unit. And And how can we do that? So here, what we do is very fast compression. And here you basically have a predefined binary masks, right? You can set up 30 of them. And when you have 30 images generated, you just multiply or superimpose your binary mask to it. And you have 30 new images and you just add them up together, right? This is a very simple operation that FPGA can basically perform very fast, low computation, low latency, right? So you can basically preserve your data stream without having to sacrifice, being sacrificed by your FPGA speed, right? And then the question is, how can you decompress it, right? This is actually called a compressed-sensing problem, right? So mathematically is a so-called a low-rank problem. So if you can find a transformation and so that your data can be transformed into a low-rank form, and then in principle, you can solve this problem, inverse problem, without losing any information. However, that finding that solution, conceptually sounds great. The mathematician, they can give you all kinds of theorem. But in practice, you find you always need to use a regularized optimization process to actually get back to those frames, and they're very slow. And here, what we have done is actually encode the inverse problem in a neural network. And here we have been very successful in doing that. One of the things is that this is a time stream problem, and meaning the next frame and the previous frame typically has correlations. Then what you can do is to use some of the time series analysis on those network RNN cells and put them into the network. That will help recover those EM images that were previously compressed and together. And here, the inference speed is very reasonable. Typically, we can compress 30 frames every second. That is a very good speed. You can think about, most of the detector can only generate 30 frames per second, and we can actually decompress it, 30 frames per second. That's very reasonable, right? Here's a compression comparison of the temporal compression algorithm we have compared with JPEG. And you will find our results. This is our result. This is the input. And this is, coming from the detector. You will find that our results has a smoothing effect, right? We didn't actually train the neural network with any smooth data, right? This is a reviewer actually asked that, where the heck did you get the smoothing effect? You didn't have it in your training data. Well, this is a very interesting thing about neural network. Because we're actually working on an inverse problem here. And as soon as you put noise into the process, you find you would not have an exact solution to this inverse problem. You would never have an exact solution to that. So that means for this optimization problem, you need the regularization terms such that it can converge to a unique solution, right? So basically this training that we did, neural network training, is to learn those regularization terms. And such that it actually, in this case, it would do some smoothing and very reasonable smoothing. And just to compare with JPEG that has the same compression ratio, and you can see JPEG has all of these artifacts, obviously. And statistical wise, our method is better signal noise ratio and higher structural similarity index. All right. So everything I showed so far, two-dimensional images, but three-dimensional object, sometimes you can get confusing results from two-dimensional projection. That's where you need a tomography experiment. And how that's done in the TEM is by rotating the sample, and you take images from different views and you reconstruct it together. How it works conceptually is like this. You have 2-point objects and take a projection image from one direction, second and third direction, right? And then in the so-called reconstruction projects where you have back reconstruction, you basically run the intensity backward. And here, right, you see a lot of stray intensity, but you actually know that the prior knowledge is that you have 2-point object, then you can actually reconstruct it, right? This is where actually, and then you need more projections to actually give you faithful reconstruction. On the left is original object. On the right are the images that has been constructed from 3 different directions. And if you add more tilt, more projections, then typically around 70, you start seeing a reasonable reconstruction, right? So mathematically, this is adding more equations for this optimization process, or for this inverse problem, right? So another thing that we have in the TEM is that we only have a limited tilt range. And that's basically illustrated here. And you're not able to tilt to very high angles because it will hit the machine, right? And then that's the problem where you have an artifact when you do reconstruction. And because we have only can tilt to a certain angle, you are missing a lot of projection information. At those high tilts, you will lose information in the Fourier domain. That's where you have the missing wedge. And if you reconstruct that, you have all this artifacts that coming from that. Also, you know, these are so-called the ghost tails. You have an elongation of objects, and these are the ghost artifacts that we typically see, right? So where does this come from, right? So I'm going to illustrate it with this little you know, teaser problem. And here is like a, you know, a tomography experiment. I set up, you know, the experiment such that the sum of those elements that you put in need to be equal to 7 in the vertical direction and equal to 11 and 10 in the horizontal. And here I'm going to have a little bit of constraint here. I'm only going to allow you to use 2, 3, 4, 5, 6 in this problem. Right, so I think all of us can solve this fairly easily. 1 plus 6 is 7, 5 plus 2 is 7, 4 plus 3 is 7. And you check that horizontally is sum up to 10 and 11 as well. Right, bingo, we solved it. Pretty easy, right? So, but hey, so this is where mathematician will come in and telling me that you are stupid, right? Is that you find, okay, the solution is now unique because these two equations are actually linearly dependent, right? So you won't have a unique solution. And basically 5 plus 2 and 3 plus 4, they can be swapped and it will still be the same solution to the problem, right? This is exactly the problem why we have these artifacts in this reconstruction when we don't have, we don't take images that's, you know, of the sample that rotate to high angle. You basically have a mathematically ill-defined problem. You don't have enough constraint. And then when you try to solve the inverse problem, you have millions or trillions of solutions. And our reconstruction algorithm only gives you one of those solutions, right? And that solution actually does not conform to the original object, right? So the question is, how can we take one solution that's reasonable, that looks similar to the previous one? Traditionally, what's been done is to use regularization terms. And here I'm going to show you actually can do it with machine learning. So you don't have to specify the regularization terms mathematically. Everything is embedded in your training data set, right? So one way to actually look at tomography data is this way, right? You have an object rotating around the axis, you're taking projection images. And if you actually plot it as a function of rotational angle, right, you find that this image actually follows a sine curve. That's called a sinogram in tomography or in CT. right? So essentially, when we have limited tools, we're basically having this sinogram, and some of that information is lost, right? So in the case, we know that this is a single object, and it has to follow a sinogram, a sine curve, then you can actually in-paint this information, right? You just fit a sine curve, voila. Your information or missing information is in-painted, right? So I'm just showing you here that if you have prior knowledge of your system, you can in-paint the lost information, right? So, okay, but however, once it goes to a reasonably more complex object, then you find that if you miss information here, right? So basically these information are lost. You can't use any very simple, linear or quadratic, cubic interpolation to actually recover the information here. However, we do map this problem to a in-painting problem, right? So how can we solve this in-painting problem, right? So here is what deepfake technology now can do. It can swap out the face of, for example, amine atoms and change the nucleus cage. And it does it very well, right? So deepfake is very powerful, and California has banned the use of that for many reasons. So however, just from technology point of view, the thing that's actually enabled deepfake is called generative adversarial network, has solved one of the most in-painting problem in computer vision, right? So we're going to utilize that. We build a GAN network where you have a forger network and an investigator network. They compete with each other until it reaches Nash equilibrium. Right? Typically, if you when we in the previous examples I show, we only have a forger network, generative network. We don't have the competing network that actually helps the forger to become better. But in this one, we added that. And then here we can actually in-paint the information that's missing here. It looks by eye pretty good compared to this one. However, we need to put it in a real test that is basically reconstructed. And here you find there are still some of those ghost artifacts, right? You have these streaks on here, you have this arc here, right? It's not very satisfactory, right? So when I first saw this, I was like, I don't like it. Kind of a failure, right? Isn't it? But then we realized actually, you can actually piggyback the first network, the in-painting network, by the second one is called artifact removal. You can still view it as in-painting network. It does one more thing, is basically recognize where the artifacts are and in-paint the information in there, right? Then once we do that, artifact removal network can actually remove all of these artifacts that was left by these residual and because the infilling wasn't done correctly, right? So this network performed very well. Here are a couple of examples. The one that I really like are here. So the traditional algorithm has very blurred boundaries, or all kinds of artifacts, but with our method, all of that can be in-painting. The artifact can be eliminated, right? So one of the things is, we always benefit from the reviewer asking questions. And here's one example. So they ask us, okay, you have two separate, parts. One is doing the in-painting in the sinogram. The other is doing the artifact. What if you have them operate on the images separately and see their effects? And we did that according to their advice. And we found actually the artifact network works pretty well just by itself. It doesn't really need the in-painting network much to actually, for example, to recover these information here, right? So that's actually a very good news, meaning that we don't have to actually develop a network to actually go into the sinogram domain, right? Because the sinogram domain, how the data is structured is depending on how you acquire the data. Everyone acquired the data differently. And then that means you have to design an in-painting network differently for for different, data type, or different people, how, their habits, right? That's not a very good ways to design a network that will work for everyone, right? So that's where we design a single scale frame again network just to operate on the reconstruction domain, the tomogram domain, right?
Huolin, so 5 minutes.
Only 5 minutes left. Okay, that's good. I'm gonna rush through. So we've done that, and it works pretty well. Even with 80 degrees of missing information, you can reconstruct the data, and you can actually increase your information content and even double it, allowing us to achieve 0.7 angstrom resolution. Right. So, and of course, we're working on this direction. And here's we learn from Apple's Deep Fusion, and of course Google's Deep Fusion as well. So here we're basically going to slightly higher dimension manifold. You have images from reconstruction by different method, and fuse them together and give you one ultimate a good outcome. And only 3 epochs training will already show improved results compared with our previous network, right? So, and can we do better? So we can have 2 domains, one sinogram, one is tomogram, and so we can actually put them together, and we build a network that's too complex. It takes half a year to train the network, so we give up on that. And then we actually look into it a little bit, find this so-called cycle GAN network. You can think about it working this way. You have a cute cat, and you describe it as a kitten wearing cat, and then you have another generated network that create this, the head in the cat. Is this book already banned? And anyway, but that's actually where you have sinogram, tomogram, and sinogram. That's actually doing the same thing, and this network performed very well. And we're really trying to actually learn from Google, so where they have the policy network, the adaptive learning that can actually create a neural network to play the Go game. Here for our reconstruction, we have different method. I'm not going to go through that. And essentially, this is a kind of a policy network process where you can choose a method or multi-method to reconstruct it. You can choose different tuning methods. And after you go to the tomogram, the same thing. You find that what you want to do in the next step is only dependent on the outcome of the last one. So this is a Markovian process. It fits the reinforcement learning very well. So we're working on that. All right. So I'm going to end my talk by showing this. All models are wrong, but some are useful. Thank you very much. So, of course, I want to thank all my funding agencies and all the collaborators, students, postdocs.
Thank you, Huolin. Maybe stop sharing so we can.
Okay.
Great, thanks. Okay, so let's thank Huolin. Toward the end there, can I ask, it seemed like you developed your methods and then Deep Fusion had sort of come along while you were doing it. And then you were immediately thinking you could do better. So is that like an issue where, just by the time you've got it going, then you need to update because the change in what's available?
Maybe can you rephrase it? I didn't quite get what you were asking.
So you were saying you have your sinogram and tomogram and sinogram, but it seemed like you had sort of gotten things working, and then you realized these Deep Fusion methods could do better, and then you had to build them in as well.
Right.
So is that an issue where just as soon as you've developed something, there's already some way of improving it that's appeared?
Yeah, well, that's a very good question for publishing. Yes, then you realize you already So this is where if a PI doesn't, schedule the publication in a serial fashion, then you will find that you have scooped yourself
Right.
in a publication that you should have waited a little bit to publish. But other than that, I think yes, we're constantly finding improvements and finding better ways to do these things, right? Just like everyone else.
You mean with the machine learning kind of?
With machine learning, yes, we constantly, try new things, and every time we try new thing, we'll find it perform better than our last one.
Right. Well, usually, let's say. And then do you have a sort of user base of people using TEM that are now using these algorithms?
Yes. Yes. So our TEM ImageNet process and the AtomSegNet models, everything we have created, those so-called baseline models for everyone to use and benchmark their methods are available to everyone. So it's on GitHub. I have a project webpage for it. And it's the TEM community is starting to use it because I have feedback from a few people like Paul Voyles. They said, okay, my network are the best, and
Right.
so.
Right, and you'd mentioned this issue about the. I mean, there aren't so many of these TEMs around the place, right? That, but you're saying each one is slightly different, right? And you were saying you'd have to retrain, whereas one of the methods sort of generally gave you good results right out of the box, right?
Yeah. So I can address this. So typically this is where the data augmentation, where the simulation show you have to put in most of the realistic noise term in it. And one of the things we realize, for example, if it is just random tearing, rather than you put in a periodic tearing, typically these tearing noises come in periodically, and that's because a dirty pump in your ground loop has like 20 hertz, something like that.
Right.
If you don't put that periodicity in there, your network does perform worse than the one that you do put in. So augmenting your data such that it adapt to all type of environments that you can think about is very helpful. But there are always situations where there are things you haven't thought about.
Yes.
And this is where transfer learning come in, adaptive learning come in. Where you need to fix this, the labels a little bit. It's very quick. It's actually, you only need to use human-assisted method to, for example, paint a few images and then use transfer learning to quickly adapt to the new type of images that you're working on. Then you're fine.
Okay, so you don't have to go through the whole network again to retrain everything. You just
yes,
one layer or so, and then it'll work as well for different TEM setup as
different TEM, and you can even make it perform better for a specific crystal structure. That's not necessarily a good thing because I'm creating a general network that's supposed to work on no matter what your crystal structure is. But if you want to constrain it such that it will perform much better on your selected crystal, you can do transfer learning on that specific data set. That's actually another thing that we're creating next is okay. I want to transfer learn this on a selected set of a crystal, and then I will allow the users to actually select them and quickly generate a data set and quickly train it. And you can deploy it for your specific image you're looking at.
Okay. Do we have questions from the audience? I think people maybe running off. One other question I have is, I mean, and this is a problem I find, like, does the fraction of your time spent on the machine learning just keep growing and growing? And you don't get to do any microscopy anymore? or any real sort of what you would consider real TEM stuff that you used to do?
Well, there are two steps. One, first, these tools, AtomSegNet models we have trained and provided everyone. Oh, that is a really good tool. So we have demonstrated that if you have a lousy TEM that doesn't provide very sharp, crisp images, they work really well, and we have been publishing using these tools. As long as they provide original image in the supplementary, that's fine. And it's a great help for my postdoc to actually go in and look at the detail of particular defects inside the materials. An under-resolved image is something that's really we don't want to look at. And the second thing is, of course, in the future, I want all of these images taken by a machine without having to even train a student or a postdoc to do that. Why not? Because we're scientists, we're supposed to focus on science, not tools. So I would very love to spend my time working on science problem rather than be a lab monkey.
I see. So basically, for everything that you're doing now, this image processing is so helpful that you use it for just about every project you would.
Yes, pretty much so.
Right.
Pretty much so.
Okay, so I mean that's very important, right? Because it gives this idea of just how useful it is in this domain, right?
Yeah, it is.
Just like with, I guess, some of the astronomy applications,
Yep.
there will be people who just couldn't possibly go back to before because it was so labor intensive or the resolution is so bad, right?
Yeah.
Yes. Okay. Okay. So thank you very much for the return visit.
Yeah. Thank you again, and I hope we have a good recording of the session. I think that's the more valuable part of this, so other people have an opportunity to see it.
Yes.
Definitely.
So, yes, thank you again, and everyone who showed up.
Yeah, thank you.
All right, thanks. Bye. Have a great one.
All right.
Thanks, Alan.